Oh, yes. But for this, oh, maybe it's because like that's what it means. It's like it's a whole. I think I understand. Well, when you come up, it's just like until the volume you already saw. Or not volume for that. There's this. It's that area. Cool. What's that? I don't know that. Yeah, those are the same thing. One cave. I'm nice. Or depends on the other.
All right, page 17. Okay, page 17 here. Two cyclists leave from the same position. Cyclist A travels north at 10 miles per hour. 1 hour later, cyclist B leaves from the position and travels due east 20 miles per hour. At what rate is the distance between the cyclists changing 2 hours after cyclist B leaves? Okay, so we know it's Pythagorean theorem problem. We can start setting up our triangle. Okay, I'll call the horizontal X, I'll call the vertical Y, and the hypotenuse Z. Okay, Pythagorean theorem. Derivative. Okay, let me list out all the variables here. Okay, so cyclist A travels north at 10 miles per hour. So we know that is referring to dy dt. We know to make it positive, not because he's going north, but because what's happening to y. Getting bigger, right? It's growing. That value, that length is growing, so we want that rate to be positive. So dy dt is 10 miles per hour. dx dt, cyclist B leaves from position, travels due east at 20 miles per hour, not because we're going right, but because over time that x is growing. So we want that dx dt to be positive 20 miles per hour. Okay, so cyclist A is going to leave first. So he's going to travel 10 miles. After that, well, 10 miles per hour, but then it's 1 hour after. So he will have traveled already 10 miles before cyclist B leaves. And then cyclist B is probably at 20 miles per hour. So this is 2 hours after cyclist B leaves. So that means cyclist B has been riding for 2 hours, while cyclist A has been riding for 3 hours. And we're going to use that time to figure out how much distance they have covered in their time period. So we know that for y, it's going to be 10 miles per hour for 3 hours. So you would have covered 30 miles. Cyclist B, traveling east, has only been riding for 2 hours at 20 miles per hour. So 20 miles per hour over a 2-hour period is 40 miles. And that's the hard part. The hard part is trying to make sure we know where the cyclists are at these moments in time.
Wait, how do you know that the 20 miles an hour went with X? That wouldn't go with Z.
Well, cyclist A is going north and the cyclist B is going east. And Z is going to be the distance that grows between the two cyclists over time. So they both cyclist A and cyclist B are starting at the same point, and one's going north and the other's going east. Okay, any questions about how we arrived at these numeric values, 30 and 40? Okay, that's good. Okay, so the rest is pretty easy because now we can use Pythagorean theorem to find Z. This is going to be variation of the 3, 4, 5 right triangle, but you can use Pythagorean theorem as well. A squared plus B squared equals C squared. This will end up being 50. And then we're just trying to solve for dc dt. dc dt also ends up being positive. That should make sense because as the bicyclists are moving further and further away from each other, the hypotenuse is also growing. So we should be expecting a positive dc dt. Okay, any questions? Number 1. All right, number 2, cone problem. Water is being pumped into a cone tank, 8 feet tall, diameter 10 feet. Let me set up my right triangle.
Will you give us volume equation?
Yep, I'll give you those. All the volume surface area formulas I'll give you.
We said for like, area.
Circle, triangle, yeah, the basic shapes, yeah. We're on page 17 in the quiz review packet. All right, so small radius is to big radius as small height is to big height. Cross multiply 8r equals 5h. I still don't know exactly what variable to solve for. I'm going to hold off on solving for a variable until I find out more information. Okay, water is being pumped into a tank that is 8 feet tall, being pumped in at a rate of 3/5 cubic feet per hour. That's going to be my dVdt. The hint also cubic feet. We know that's going to be volume related per hour, volume and time. So the only variable with volume and time is dV over dt. Water's being pumped in, so the volume of the water is going to continue growing. We want it to be a positive rate. Okay. At what rate is the depth of water in the tank changing? So we're looking for dH/dt. If it was dR dt, they would say at what rate is the radius of the water in the tank changing? But here we're looking for dR dt. Sorry, dH dt.
The screen's frozen.
Oh, sorry. Okay. When the tank is half full in terms of the height. So that means when h is 4 feet. We know that there's always going to be a number that we want to stay away from uh, until the end of the problem. This is that number. We don't want to don't use until the end. All right, so here's our big hints. We're looking for dH/dt. So that tells us that we want something that is height related. So that kind of helps guides what variable that we want to keep and which variable we want to try to replace. We would like to keep h, so that h can naturally produce dH/dt, which means we would like to remove r. If I want to remove r, I'm going to solve for r so I can find a replacement for r. So r is equal to 5h over 8. Now I'm going to take that, put it into my volume equation.
Wait, how'd you get the highest of one?
Oh, it says when the tank is half full. So the tank is 8 feet tall, so half full in terms of the height. So half full will be 4 feet. Okay, so here's my substitution. So now we're off to trying to clean up our volume equation. Okay, let me pause here for a moment. Everybody okay with why we're making this decision to get rid of R and not H, and that why we want to keep H and not R?
Yes.
So whatever we're looking for, this is what is going to help guide our decision for what variable we want to keep. Okay, so once we're here, we're moving in the right direction. We're trying to eventually find the derivative, but we have to do some cleanup, right? This is not a good spot for us to find our derivative. So we're going to try to get rid of the parentheses, square whatever we need to square, merge all the coefficients together. Let's merge the variables together. It should be a nice, clean volume equation formula before we jump into our derivative step. Okay, so I'm just putting all the numbers together as a fractional value here. So 25 pi in the numerator, 3 times 64 is 192. That's in the denominator. I want to merge the h's together. So h squared times h is h cubed. So this is where we want to be before we start our derivative step. Any questions up to this point? All right, so now derivative, v becomes dp dt. Coefficient stays. H cubed, derivative, we do power rule. Now, from here, everyone may decide that they're going down a different path in terms of cleanup, so that's fine. I'm going to choose to clean up a little further here, multiply the 25 and 3 together. But if you want to start plugging in, you can, because now everything is fair game to be used. We can replace dv/dt with 3/5. We're looking for dh/dt. We see that variable waiting for us. And then now we can use that h equals 4. That 4 can now be used for h. I'm going to divide that fraction over to the other side, try to isolate dh/dt. So dividing by this fraction is the same thing as multiplying by its reciprocal. And as I plug in the calculator, I want to leave pi out of my calculator. I just know that pi is going to stay in the denominator. So whatever fraction I get after I reduce, I'll just let that fraction stay, and then just have pi stay in the denominator as well. Okay, units of measure, feet. Height is in terms of feet. Time is in terms of hour, so feet per hour. Okay, page 18. Any questions with this? Okay, radius of a circle increasing on a constant rate of 0.2 meters per second. What is the rate of increase of the area of a circle at the instant when the circumference is 20 pi meters? So let's go ahead and find all the derivatives that we need. Okay, we may not need everything, but let's just have it there in case we need it. So A becomes dA dt, pi r squared becomes 2 pi r dr dt, C becomes dc dt, 2 pi r becomes 2 pi dr dt. All right, radius of a circle increasing at a constant rate of 0.2 meters per second. You know, that's dr dt. Increasing, so positive rate. What is the rate of increase in the area of the circle? So we're looking for dA dt. When the circumference is 20 pi, so that's C equals 20 pi. Okay, so I want to solve for dA dt. To solve for dA dt, I need r and dr dt. Well, the nice thing is we have dr dt, so we can go ahead and plug that in. But we're missing r, so how can we get to the radius? Use circle. There we go. Yeah, so it looks like I have more information than I need. I don't really need that dc dt. If I just use that circumference, find the radius, and that's enough. But I just had this in case I needed it. All right, I have my radius is 10, I have dr dt is 0.2, and now I have everything that I need to solve for dA dt. All right, I'm multiplying everything in the calculator. I'm just leaving pi out of the calculator so I can have exact value. So 2 times 10 is 20. 20 divided by 5 is 4. Okay, units of measure. Let's figure out the units for area. We'll find the units of measure for time, and we'll divide them over each other. Area is a two-dimensional unit. So area is what?
Meter squared.
Meter squared. Good. Meter squared. Time is seconds, so meters squared per second. Right, number 4. Any questions with 3? Okay, number 4, cylinder tank. We know cylinder is going to be an easier problem than cones, but sometimes we have extraneous information. We want to make sure we don't let that distract us. Okay, cylindrical tank has a height of 16 feet with an area of the circular base being 25 pi square feet. So, you know, the circular area here. It's 25 pi. Water flows at 8 cubic feet per minute. We know that's dV dt. How fast is the water level rising? We're looking for dH dt. When the tank is half full. So the height is, the water level is going to be 8, but we may not even need this. Okay, so we know that the nice thing about cylinders is that if I can figure out what the radius is, I can go ahead and replace it because that radius is never going to change, right, for that water level. So my volume formula is pi r squared h. If I can figure out what radius is, I can get rid of it. There's no similar triangles. I can jump directly into my derivative once my radius has been found out. So they don't tell me the radius directly, but they do tell us the area of the circular base. We know area of a circle is pi r squared, so use related information to help me get to the radius of this cylinder tank. Divide both sides by pi. R squared is 25, so therefore my radius is 5. The radius of the tank is the same as the radius of the water level. The water level is always going to stay at a radius of 5. You can imagine that water level rising and falling, that radius is never changing. So there's no need for us to hold on to that variable, unlike cones where radius and the height of the water level are continually changing. So V is equal to pi 5 squared times h. We only have one variable on the right side. We can move into our derivative step immediately once we get our radius taken care of. Okay. B becomes dv dt. 25 pi stays. H becomes dh dt. Okay. Start plugging in. dv dt is 8. We're looking for dh dt. We don't need the height of the water level. We don't need the height of the container. So these are extraneous information, good for cones, but not needed for cylinders. Okay, height is a one-dimensional unit, so height is feet, time is minutes, so feet per minute. Notice I is staying in the denominator here. Page 14. Let me do a limit problem and a linear approximation. So problems number 6 and 7, bottom of page 14. Okay, first thing we do with a limit problem, we always do direct substitution as our first step. So replace all the x's with 1. Okay, we get 0 over 0. That tells us that there's a hole. The limit does exist. But we have now the ability to do L'Hopital's rule because we have the condition that is needed for L'Hopital's rule. So we take the derivative of the numerator, take the derivative of the denominator, reevaluate. We have a real number. There's nothing more to do. That is our limit. All right, what if we get 0 over 0? We did L'Hopital's rule. We reevaluated, and we still got 0 over 0. Do it again. Yeah. So make sure that we only do L'Hopital's rule a second time if we get a second set of 0 over 0. Right? We don't want to keep finding the derivative over and over again until there's nothing, until we're left with constants. That it may not always lead us to the right answer. So make sure that if we want to do it, if we were going to do it twice, we need something to tell us to do it a second time. Okay, 7 is worded a little differently than I would ask on the quiz. So let me reword number 7. Okay, so linear approximation is we want to create our tangent line equation, but tangent line equation, we want to find the nearest integer value so that we can build a nice tangent line equation, and then we can use 8.04 at the end. So what x value do we want to use as our center of our problem? 8, yeah. So find the closest integer value. That's going to be your x value. So that means we want to build everything at x equals 8. All right, so we're going to find our order pair at x equals 8. We're going to find the slope at x equals 8 through the derivative, build our tangent line, and once we build our tangent line, then the 8.04 gets inserted into our tangent line equation. Oh, if the problem tells you that the graph is concave down or concave up, then at the end, you can tell me whether that approximation is over approximating or under approximating. But I will tell you whether it's concave up or concave down. You don't have to find it out yourself. Okay, let's finish this piece first. So if I want to find the derivative, I have to get it ready for power rule. So cube root of x is the same thing as x to the 1/3, but x to the 1/3 in the denominator is still out of place. I'm going to push it up to the top, make it x to the negative 1/3. My derivative, now I can go through power rule. So bring down the exponent, subtract 1 from the exponent. So negative 1/3 minus 3 over 3 is negative 4/3. Do a little bit of cleanup. Find my slope. Cube root of 8 is 2. 2 to the 4th is 16. Okay, so I have everything that I need. I have my ordered pair. I have my slope. I can now do point slope form. Let me get y by itself. So the hardest part is always just the finding that tangent line equation. After that, then the approximation is easy because you can just plug that 8.04 in for x. Okay, let me do a part B for this problem here. Given that the function is concave up at x equals 8. Okay, so I'm telling you the graph is concave up. The concave up looks like this, which means that any linear approximation is going to be what? Under, yeah.
Why would you put this slope as a negative slope? Like, like.
No, you're right. Yeah, negative slope. You don't have to draw it. I just want to, it doesn't matter where we draw our tangent line. It's always going to be under approximation, as long as it's concave up.
You're gonna have to write it like that in ways.
No, you just say that the function is, you just say that the approximated value is under approximation or over approximation. You don't have to show any work per se. Okay, let's do a shadow problem. I don't have one here, so I'll just create one. You guys want to just grab a sheet of paper and just
Yeah, it's good. Just give me the data stuff on
He said from here, so I'm sure you can. No, it's all.
Mhm.
We need to know the surface area looks like.
No, I'll give you volume and surface area formulas. It's negative. Here's. Just. So you could do. Okay, a man 6 feet tall walks towards a lamppost, 17 feet tall. Man walks at a rate of 3 miles per hour. At what rate is the tip of the shadow moving when he is 5 feet away from the lamppost? Okay.
Okay.
Towards. We're always going to set it up this way. Where your vertical will be your constants, and then your horizontal will be where your variables are. It's always going to be y over x plus y, not x over x plus y. Cross multiply. Okay, 6x equals 11y. Any questions so far? Okay, we find our derivative. Time is going to impact both of our variables there. Okay, let me remind us what each of the variables mean. So dx dt represents the rate of change of the person walking. Dy dt represents the rate of change of the shadow length. And then finally, if I add the two rates together, dx dt plus dy dt, that will be the rate of change of the tip of the shadow. Okay, so we have information about dx dt, right? What's dx dt going to be? -3 because he's walking towards the lamppost. X is shrinking. That distance between the man and the lamppost is decreasing. So we want dx dt to be -3. So we take that, insert into our derivative equation. We can solve for dy dt. dy dt is the rate of the shadow length. It's not what the problem is asking, but we do need that information to get a tip of the shadow, because ultimately we need to have both sets of information so we can add them together to get the tip of the shadow. Okay, so we have the rate, the person's walking, we have the rate at which the length of the shadow is decreasing. We add those together and we have the rate of change of the tip of the shadow. Notice that this 5 feet is not used. The derivative doesn't need how far the person is away from the lamppost. So this is extraneous data. We don't need that 5 feet away from the lamppost. Over 11, sorry. I'll copy the wrong. Do you guys get that? Negative 51 over 11. Okay.
If it's like repeating, decimals, we write it fraction.
Yeah, so you can always hit math fraction to get your repeating decimal to a fractional value. Math 1. Okay, I'll come around and see if you guys have any individual questions for me. There is no variable. There's just now, if you want to go to product rule, you can. You don't need to because that is a constant. You can still do f prime and f prime. It's just one of them. One of the product rule terms will drop out to be 0 because that counts.
Like something that's on the test, you're like, okay, so I was doing it last time, I didn't come up with this. That's, it's so interesting, like the stuff we do.
Like 4.25. It's all I do this for my own personal. Looking in opposite directions, so I want to create just one time. I want to create one movie, then the other show. Well, yeah, you have two races together, so the information is still the same, but you only have one vote moving. It's staying the same, so it's just one.
Actually, I thought he was gonna really. Sweet. So if I do that, something like. Yeah, I did. Maybe you got straight, like, no, I would like.
Right here, but my brother got someone else over and I showered on like I got there and then I was thinking about getting out and my dad drives like to school, so like well, that's the thing later, we don't have to do it. And so it's like easier because I don't.
It's just fine to read.
Yeah, no, like I'm gonna go straight to the school, at least segregation. Yeah.
We have eight.
And they're like, no, that's fine, it was 2 a.m, I was
But if
sending.
you want, you already.
You know what, I'm not running to run, I don't care, so, show up, and I didn't that's how they get sick, I'm sorry, like, I was be right, and we're just. Yeah, I look foul, there's just a difference between. I actually,
Yeah, I would say this is.
I couldn't do it. Yeah, I'm just like, I'd rather just.
Focus on trying to find the already.
Just for, values.
Because.
No,
Is,
No, me too.
I'm already changing. Going.
But I just, yeah, that's.
Focus on
I
finding
put
the already team.
in, like, state on Wednesdays or then I swear I did 50 rounds. So you get all. I got all this morning, right?
You already.
All the just double. Yes. So I'm like, you know what? Yeah, I tried not to, especially as I'm getting very nice, it's the next one I know.
So if you think about this. The ladder is 17 feet tall. Or 7 feet.
Yeah, so.
As
That's what's makes it over and over.
It's gonna stay 7
I just read like, I was just believe about writing, and I always see this.
Yeah.
Oh.
It's like a good question, like,
I know, I'm.
No.
So like, I'm assuming people are now, but this first, like, what page of this one of you, like,
Yeah.
this one, oh my goodness gracious, okay, perfect.
have what?
Yes. Okay, I was going to. Oh, yeah. It's 12:30, Are you doing that here? Yeah, I'm doing it here. I'm gonna go here.
Yeah.
All in.